The Riemann hypothesis is a conjecture about the pattern of prime numbers, but it's too simple and slightly misleading. Let's make this sentence more accurate.
First, what do we mean by the pattern of prime numbers? Primes appear irregularly, but the Riemann hypothesis does not tell us exactly where the next prime will appear. It is not a formula that predicts every prime. Instead, it is about how many primes there are. So we have about the number of prime numbers. That's better. The Riemann hypothesis is deeply connected to the following question. How many primes are there below a given number x? We write this as pix, the prime counting function. Long before Riemann, mathematicians already had a way to estimate its value. As x becomes very large, the number of primes below x is approximately x divided by log x. An even better estimate is given by the logarithmic integral Li of x. This captures the average distribution of primes. Unlike the seemingly irregular positions of individual primes, their overall distribution follows an underlying pattern. But the prediction is never perfect. The predicted value and the actual value are always slightly different. That difference is what the Riemann hypothesis is really about. So we have about the difference between the predicted and actual number of primes. We call that difference the error. Then we ask, how large can that error become? This is the question the Riemann hypothesis is really asking about prime numbers. So finally we have the Riemann hypothesis is a conjecture about how large the error can become between the predicted and actual number of primes. But surprisingly, the actual statement of the Riemann hypothesis never mentions prime numbers, the number of primes, or even the error. Instead, it talks about the zeros of the Riemann zeta function. So we first need to understand what the zeta function is. It was originally defined using all natural numbers. Remarkably, the very same function can also be written entirely in terms of primes. This tells us that the zeta function contains information about every prime. Using this function, Riemann developed an even more accurate prime counting function, and in the process, formulated the Riemann hypothesis. Specifically, zeros are the complex numbers where the zeta function equals 0. Among them, the non-trivial zeros have real parts between 0 and 1. On the complex plane, these zeros lie in a region called the critical strip. By calculating the first several non-trivial zeros, Riemann discovered that they all lay on the line whose real part is 1/2. He then made a remarkable conjecture. Perhaps every non-trivial zero has real part 1/2. It means they all lie on that same line. That became the Riemann hypothesis. Then why does that matter? Because those zeros determine how the error between the predicted and actual number of primes fluctuates. Each non-trivial zero contributes a wave-like fluctuation to the error. The total error is determined by the combined effect of all those fluctuations. Now imagine that every non-trivial zero has real part exactly 1/2. Then the error remains roughly on the scale of square root of x. The actual number of primes never strays too far from the prediction. In other words, the distribution of primes stays relatively close to the overall pattern predicted by Lie x. But if even one zero has a real part greater than 1/2, its contribution becomes much larger, and the error could grow far more than we ever expected. This means that the distribution of primes could, at times, deviate much more dramatically from the overall pattern predicted by Lie x. In some regions, there could be far more primes than expected, while in others, far fewer. And this is why the real parts of the zeros matter. They determine how large the error can become. This tells us how much order lies beneath the seemingly irregular distribution of prime numbers. The Riemann hypothesis is stated in terms of the zeros of the Riemann zeta function, but those zeros tell us something about prime numbers. The Riemann hypothesis is really a conjecture about how large the error can become between the predicted and actual number of primes. And ultimately, it is really about the distribution of prime numbers. Please like, comment, and subscribe to support this channel. Thanks for watching.